Have you ever looked up at the night sky and wondered, does it go on forever? Welcome to Boring Stuff, where we slow things down and explain what we know. In this video, we explore whether space has an edge or if it might be infinite. Step by step, we'll look at ancient ideas, modern theories, and what science can tell us. We live on a small planet, orbiting an average star, tucked into one arm of a galaxy that is one of billions. When we look up at the night sky, what we see is only a fraction of what's out there. But no matter how far we look, the same question always seems to return. Does it ever end? Is there a final edge to the universe? A point where space itself simply stops? It's a question that seems simple, but quickly becomes difficult to answer. That's because when we talk about space, we're not just talking about stars and planets. We're talking about the structure in which all those things exist. Space is not just empty distance. It's part of what the universe is made of. If you walk across a room, you're moving through space. That space is defined by length, width, and height, the three familiar dimensions. But what's outside that room? Another room. What's outside that building? The street. What's outside the city? Eventually, the horizon. On Earth, we can always move further in a direction until we run into something. But is the universe the same? We're used to the idea that everything must be inside something else. A box in a room in a house on a street on a planet. But when it comes to the universe, we have to ask, is the universe in something else? Or is it all there is? One way to think about this is by imagining distance itself. When we measure kilometers or miles, we're measuring how far apart things are in space. But if there's an edge to the universe, what would be on the other side of it? If you could reach the final star, the last planet, and go just a little farther, what would you find? More space? A wall? A blank void? This is where we run into the limitations of our intuition. We evolved on a small planet, dealing with objects we can see and touch. Our everyday experience tells us that space is something we can move through, and that everything must end somewhere. But in cosmology, the study of the universe as a whole, those ideas start to break down. When scientists talk about the universe, they distinguish between what we can observe and what might exist beyond that. The observable universe is the part we can see, because light from those areas has had time to reach us since the universe began. That distance is currently estimated to be about 46 billion light-years in every direction. So the observable universe is a sphere around us, roughly 93 billion light-years across. But that doesn't mean that's where the universe ends. Beyond that sphere, it's likely that more space continues, possibly much more. But we can't see it, because the light from that region hasn't had enough time to reach us. It's not that there's a wall or an edge, it's just that the information hasn't arrived yet. The limitation isn't space ending, it's light travel time. So the first thing to understand is that when we ask, does space end, we have to separate what we can observe from what might be out there. The universe could be much larger than what we see, possibly infinite. Or it could be finite but unbounded, a concept we'll return to later. Another important point is that space is not static. The universe is expanding. That means galaxies are moving away from each other over time, and the space between them is growing. This isn't because galaxies are flying through space like bullets. It's because the space between them is stretching. Space itself is growing. This changes how we think about the structure of the universe. If the universe is expanding, what is it expanding into? The answer is nothing. It's not expanding into a pre-existing space. Instead, space itself is growing. Imagine drawing dots on a balloon and then inflating the balloon. The dots move apart, not because they're sliding on the surface, but because the surface itself is expanding. There's no edge to the surface of the balloon. It loops back on itself. It's finite, but you can never find a boundary. You can walk in any direction forever without falling off. That balloon example is only an analogy. It describes a two-dimensional surface expanding in three-dimensional space. But in cosmology, we're talking about three-dimensional space expanding over time. We can't visualize that directly, but the math is similar. It's possible for space to be finite and unbounded, meaning it has a limited volume but no edges. That's one of the possibilities for our universe. On the other hand, space could be infinite. That's another scenario that fits the current observations. In this case, there is no boundary. No matter how far you go, you'll always find more space, more galaxies, more stars. You could travel in a straight line forever and never reach a wall. That idea is hard to grasp because it contradicts our everyday experience. We're used to things ending. But in mathematics and physics, infinity is a valid concept, as long as it matches the evidence. So far, the evidence from cosmological measurements, such as the distribution of galaxies, the cosmic microwave background, and the geometry of space, suggests that the universe is either flat and infinite, or very large and curved in such a way that we can't detect the curvature. But that doesn't settle the question. We only have access to the observable part of the universe. If space does curve or loop back on itself, it might do so beyond the regions we can see. It's also possible that space has a more complex topology, just like a video game map that wraps around when you move off the edge. Some models of the universe suggest that space could be multiply connected, meaning that if you travel far enough in one direction, you might eventually return to your starting point. That would make space finite, but still without edges. Again, this is difficult to visualize, but it's allowed by the laws of physics. So when we ask if space ends, we have to understand that the question might not have a yes or no answer in the way we expect. The universe might not have an edge like the edge of a table. Instead, it might be infinite, or it might be curved in such a way that there are no boundaries, only continuous motion. From a scientific standpoint, the current models allow for both finite and infinite universes. What matters is how well those models match the observations. So far, the data is consistent with both possibilities. We don't yet have a way to measure what lies beyond the observable universe, so we can't say for sure. That leaves the question open, which is part of what makes it so interesting. The more we study space, the more we learn, but also the more we realize how much we don't yet know. Asking whether space ends is not just about physical boundaries. It's about how we define space itself and whether our concepts apply at the largest scales. Some physicists argue that the question of whether the universe is infinite or not might be unanswerable, at least from within the universe. If we're stuck inside the observable bubble, we may never know what lies beyond it. But that doesn't stop us from building models, testing predictions, and refining our understanding. The question also touches on deeper philosophical ideas, like whether the universe has to have a size, or whether infinity is something that can exist in nature. Is space something that can exist without matter, or is it always defined by the things inside it? Does empty space have properties, or is it just nothingness? These are questions that blend science and philosophy, and they remind us that the boundary between the two isn't always clear. When we ask whether space ends, we're really asking what kind of thing space is. Is it a container, a fabric, a field, or something else entirely? And is there anything beyond it, or is beyond a meaningless concept in this context? In the end, the universe may not give us a final answer, at least not one we can observe directly. But the process of asking, measuring, modeling, and refining our understanding is how science moves forward. Even if space has no end, our curiosity doesn't stop. And sometimes, the value is not in the answer, but in the question itself. Long before telescopes or satellites, long before physics or mathematics as we know them, people looked up at the night sky and wondered what they were seeing. The sky, especially at night, has always raised questions. What are those lights? How far away are they? What holds them up? And perhaps most of all, does the sky go on forever, or is it enclosed in something? Ancient views of the cosmos were shaped not by data, but by human observation and imagination. Without tools to measure the heavens, people relied on what they could see and how it felt to live beneath the sky. From this starting point, a wide variety of models and myths were born, some symbolic, others more systematic, but all trying to answer the same core questions about the size and shape of the universe. One of the earliest recurring ideas was that the Earth was flat and stationary, with the sky as a dome overhead. This concept appeared in many early cultures, including ancient Mesopotamia, Egypt, and early Hebrew cosmology. The Earth was imagined as a flat disk, like a circular table or island, resting on water or surrounded by a boundary ocean. Above this flat Earth, the sky was a solid dome, a firm structure that held back the waters of the heavens. In some versions, the stars were embedded in the dome like tiny lamps. In Mesopotamian cosmology, the universe was thought to have multiple levels. The Earth was the middle level, a flat platform. Beneath it were the waters of the abyss and the underworld. Above it were layers of the heavens. Gods were often placed in these different levels, with the highest heavens belonging to the sky gods. This multi-tiered structure provided a clear vertical order to the cosmos, and space beyond the dome was often considered unreachable or divine. In ancient Egypt, the sky was sometimes personified as the goddess Nut, whose arched body formed the ceiling of the world. She was supported by the god Shu, the air, who separated her from the earth god Geb below. Again, the image was of a world with a fixed, limited structure. The sky was not infinite. It was something that had form and containment. The ancient Hebrew view of the cosmos was similar. In early biblical texts, the firmament is described as a solid dome separating the waters above from the earth. The stars, sun, and moon are set within this firmament. The earth is supported on pillars, and beneath it lie the waters of the deep. Heaven is not a formless sky, but a tangible ceiling. In this model, the cosmos is clearly finite and layered. In many of these systems, space did not go on forever. It ended at some point, either with the dome of the sky or with the outer waters. The cosmos was a container with walls. What lay beyond was usually not considered. The focus was on what was observable and symbolically meaningful within the visible structure. As societies grew more organized and began studying the sky in more detail, some thinkers began to propose more systematic models. In ancient Greece, philosophical approaches to the cosmos began to replace mythological ones. Yet even then, the universe was still seen as finite. The Greek philosopher Anaximander, active in the 6th century BCE, is one of the first recorded thinkers to try to describe the cosmos in natural terms. He imagined the Earth as a cylinder, floating freely in space, not resting on anything. He proposed that celestial bodies revolved around the Earth on invisible wheels. Though primitive by modern standards, his ideas broke away from the flat Earth assumption. Later, Pythagoras and his followers introduced the idea that the Earth was spherical. This view gained support through careful observation, such as the curved shadow Earth casts on the Moon during an eclipse. A spherical Earth suggested a more unified and symmetrical universe. Plato and Aristotle expanded on this. In Aristotle's model, the universe was a series of nested crystalline spheres, each carrying a celestial object: the Moon, the Sun, the planets, and the stars. These spheres rotated in perfect circles around the Earth, which remained fixed at the center. Beyond the outermost sphere of the fixed stars was the prime mover, an eternal force that set everything in motion. The universe had a limit, and beyond that outermost sphere, there was nothing, not even space. This idea of a finite, enclosed universe became dominant in Western thought for over 1,000 years. It aligned with religious views as well. In Christian cosmology during the medieval period, the outer sphere of the stars was often seen as the boundary between the natural and the divine. Heaven lay beyond it. The Roman astronomer Ptolemy formalized this geocentric system in the 2nd century CE. His model used complex combinations of circles, epicycles, and deferents to explain the motions of the planets while keeping Earth at the center. This system matched observations reasonably well and was accepted in Europe and the Islamic world for centuries. Even though these ancient models were incorrect by modern standards, they weren't irrational. They were based on what could be seen and measured with the naked eye. The sky appeared to rotate around the Earth. The stars didn't change positions relative to one another. The planets moved in complex but somewhat predictable patterns. There was no reason, based on direct observation, to assume the Earth moved or that the universe was infinite. In ancient India, cosmological ideas were also developed, though they often took a different form. Hindu texts describe a vast universe with cycles of creation and destruction lasting billions of years, remarkably close in timescale to modern cosmology. The structure of space itself was often metaphorical, with multiple layers of reality and vast distances between celestial realms. Some texts mention infinite space, though often in philosophical rather than physical terms. In China, early models of the universe also envisioned a flat Earth covered by a dome-shaped sky. Over time, Chinese astronomy became highly advanced in observational terms, predicting eclipses, tracking comets, but it did not always seek to describe the overall structure of the cosmos in the same abstract ways as Greek models. The Islamic Golden Age preserved and extended many Greek cosmological ideas. Scholars like Al-Farabi, Al-Biruni, and Ibn Sina discussed the structure of the universe, often blending Aristotle's physics with religious metaphysics. Al-Biruni, in particular, questioned the idea of an absolute center and began to consider whether space might exist beyond the known universe. The shift from ancient to modern cosmology began in Europe with the Copernican revolution. In the 16th century, Nicholas Copernicus proposed a heliocentric model, the Sun at the center, with Earth and the other planets orbiting it. This was a major break from the geocentric tradition. But even Copernicus still saw the universe as enclosed by a sphere of stars. It wasn't until the work of Johannes Kepler, Galileo Galilei, and eventually Isaac Newton that the idea of an open, potentially infinite universe gained traction. Newton's law of universal gravitation implied that objects in space influence one another without the need for celestial spheres. Space became a continuous, three-dimensional backdrop in which all matter moved, influenced by force rather than mechanical structure. Over time, the idea that the universe had edges began to fade. As telescopes improved, astronomers found more stars, more galaxies, and more space, without any sign of a boundary. The visible universe kept getting bigger, and the idea of a fixed outer shell no longer fit the evidence. Today, ancient models are no longer used in science, but they remain important for understanding how human thought evolved. They show how our ideas about space have been shaped by culture, observation, and imagination. From a dome above a flat Earth to crystalline spheres surrounding a stationary planet, to the possibility of infinite space, each step has brought us closer to understanding the scale and structure of the universe. What's notable is that for much of human history, space was seen as finite. It had boundaries, physical, symbolic, or spiritual. The idea of infinite space was not the default. It emerged slowly as observations improved and mathematical models became more accurate. Even today, our understanding of space is shaped by the tools we use and the questions we ask. As we explore further, we continue to build on thousands of years of curiosity and observation. And though the details have changed, the basic impulse remains the same: to look up, to wonder, and to ask what lies beyond what we can see. Understanding whether space ends requires first asking what kind of thing space is. To make sense of it, scientists study the shape of space, not the shape of individual objects like stars or galaxies, but the shape of space itself. This is not about what we see inside space, but the geometry of the space that holds everything. That includes whether it has curvature, how far it extends, and what happens if you travel in a straight line forever. In everyday life, we think of space as flat. If you walk down a road, you expect it to continue straight. If you look across a room, you assume light travels in a straight path. That's how space works at small scales, like in buildings or cities. But when it comes to the entire universe, this idea of flatness may not apply. The large-scale structure of space could be curved, and that curvature would determine whether space is infinite, finite, or loops back on itself. In geometry, curvature comes in three types: positive, negative, and zero. These correspond to spherical, hyperbolic, and flat geometry. Each one describes a different way space could behave over very large distances. Positive curvature means space bends like the surface of a sphere. If you imagine two straight lines starting at the same point and going in slightly different directions, they will eventually come back together. This is like how two lines of longitude on Earth start at the equator and meet again at the poles. In a positively curved universe, space would be finite, but without edges. You could, in theory, travel in a straight line and eventually return to where you started, just like going around the Earth. There's no boundary or wall. The curvature keeps space contained. Negative curvature, on the other hand, is like a saddle. In this kind of geometry, lines that start off parallel diverge as they continue. The angles in a triangle add up to less than 180 degrees. A hyperbolic space would be infinite, but its expansion would create very different patterns from those seen in flat or spherical space. It would never loop back on itself. Instead, space would keep stretching outward, creating more volume than you'd expect based on simple geometry. Zero curvature means space is flat. This is what we're most familiar with. In flat geometry, parallel lines stay parallel. Triangles have angles that add up to exactly 180 degrees. Euclid's geometry, the kind taught in most schools, assumes this flatness. In a flat universe, space can still be infinite, but it can also be finite if it's shaped in certain ways, such as a torus or other closed-loop structures. To determine the actual shape of space, scientists study how light travels over long distances, how galaxies are distributed, and how the early universe behaved. One of the most important tools in this research is the cosmic microwave background radiation. This is the afterglow of the Big Bang, radiation that fills the universe and carries information about its structure billions of years ago. The cosmic microwave background shows tiny fluctuations in temperature and density. By analyzing the angular size of these fluctuations across the sky, scientists can determine how space bends. If the universe is flat, the fluctuations appear at a certain predictable size. If space is curved, the fluctuations will appear either larger or smaller, depending on the curvature. Current measurements from missions like WMAP and Planck show that the universe is very close to flat. This doesn't mean it's perfectly flat. It just means that if it is curved, the curvature is so small that we haven't been able to detect it yet. From our position, the observable universe appears to follow the rules of flat geometry to a high degree of precision. However, this leads to another important point. We can only measure the curvature of space in the part of the universe we can observe. That's a limited sphere around us, extending about 46 billion light-years in every direction. What lies beyond that could be different. Space could be curved on larger scales we can't access, or it could continue flatly forever. Even if space is flat, that doesn't automatically mean it's infinite. Flatness refers to geometry, not size. A piece of paper is flat, but it's not infinite. The same could be true for the universe. It could be a flat but finite structure that wraps around in a complex way. This is where topology becomes important. Topology is the mathematical study of how shapes connect and behave in space. It goes beyond geometry to consider how a space can be twisted, looped, or folded without breaking. A donut, for example, has a different topology than a sphere, even though both are smooth and continuous, Some cosmological models propose that space could have a compact topology. That means you could travel in one direction and eventually return to your starting point, even in a flat universe. These models are hard to test, but scientists look for repeating patterns in the cosmic microwave background or duplicated structures in galaxy surveys as possible signs. Another way scientists think about the shape of space is by measuring how mass and energy influence it. According to general relativity, space is not a fixed backdrop. It bends and curves in response to matter and energy. This is what causes gravity. Massive objects like stars and planets distort the space around them. But general relativity also applies on large scales. The total density of matter and energy in the universe determines its overall curvature. This density is measured in terms of a critical value. If the actual density is higher than the critical density, the universe is closed and positively curved. If it's lower, the universe is open and negatively curved. If it matches the critical density exactly, the universe is flat. Observations currently suggest that the total density is very close to this critical value. But that's not the end of the story. In recent decades, scientists have discovered that most of the energy in the universe is not from visible matter or even dark matter. It comes from something called dark energy, a mysterious force that causes the expansion of the universe to accelerate. Dark energy affects the curvature of space as well. Depending on its properties, it could influence the shape of the universe in ways we don't fully understand yet. All of this shows how interconnected space, matter, energy, and geometry are. The shape of space is not just a matter of drawing diagrams or imagining models. It's tied directly to the physical properties of the universe, how it began, how it evolves, and what it's made of. Despite all these measurements and theories, there's still no definitive answer. We have strong evidence that the observable universe is flat and that space continues beyond what we can see. But whether space loops back, stretches forever, or has some other structure remains uncertain. The difficulty comes from scale. We're trying to study the shape of something so vast that we can only observe a fraction of it. And even that fraction is limited by the speed of light and the age of the universe. It's like trying to determine the shape of an entire planet by standing in one spot and looking around. You might guess it's flat, but that doesn't mean it is. Scientists continue to refine their measurements, looking for small deviations that could indicate curvature. They also develop theoretical models that explore different possibilities. Some models predict that space is truly infinite. Others suggest it's closed, like a higher dimensional sphere. Still others leave the question open, focusing instead on what can be observed and tested. In the end, the shape of space is one of the most fundamental questions in cosmology. It affects everything from how galaxies form to how time flows to whether the universe will expand forever or eventually collapse. Understanding the shape of space helps us understand the structure of reality itself, not just what's in the universe, but how the universe is put together. The fact that we can even ask this question and begin to answer it through observation, mathematics, and theory is a reminder of how far human knowledge has come. We started with simple observations of the stars and planets. Now we measure fluctuations in radiation from the early universe to map the curvature of space billions of light years away. And yet, the question remains open. The shape of space may be flat, curved, finite, or infinite. We don't yet know for sure, but we continue to measure, model, and imagine. Because even if space has no edge, our curiosity does not. One of the most helpful ways scientists explain the large-scale structure of space is through an analogy involving a balloon. This model helps illustrate how space can expand without requiring an edge, and how something can be finite in size yet have no boundary. While it isn't a perfect representation of the universe, the balloon analogy offers a starting point for understanding some of the most confusing parts of modern cosmology. Imagine a regular party balloon. Before it's inflated, it's small and wrinkled. But as you blow air into it, the balloon expands. Now think about the two-dimensional surface of the balloon. Not the inside, not the rubber itself, but the outer skin. That surface is curved in 3 dimensions. It has area, shape, and distance. And as you inflate the balloon, that surface grows. Any 2 points on the balloon's surface move farther apart as more air is added. Now imagine placing tiny dots on the surface before inflating it. As the balloon expands, each dot moves away from the others, even though none of them are moving on their own. It's not that the dots are sliding along the balloon. The surface itself is stretching, and the space between them increases. This is where the analogy connects to the universe. In the balloon model, the surface represents space, not the inside of the balloon, just the surface. Our 3-dimensional universe, in this analogy, would be like the 2-dimensional surface of the balloon. When scientists say the universe is expanding, they don't mean galaxies are flying outward into empty space. They mean the space between galaxies is increasing, like the distance between dots on an inflating balloon. One important idea here is that there's no central point of expansion. Every dot on the balloon sees all other dots moving away from it. No matter which one you stand on, you would think you're at the center. The same is true in our universe. Every galaxy, from its own point of view, sees other galaxies receding. There is no privileged location where the expansion started. The expansion is not into something. It's the fabric of space itself changing. This helps address a common misconception. When people hear that the universe is expanding, they often imagine a blast, like an explosion, where matter flies outward from a central point into empty surroundings. But that's not what's happening. There is no edge into which the universe is expanding. Instead, every part of space is expanding. The distance between distant galaxies increases, but there is no border beyond which the universe is growing. The balloon analogy also explains how space can be finite yet have no edge. The surface of the balloon is a closed shape. If you walk in a straight line on it, you'll eventually return to your starting point. There's no boundary or wall, but it doesn't go on forever. It's finite but unbounded. Our universe could be similar, a 3-dimensional space that loops back on itself in a higher dimensional way. In this model, asking what's outside the universe is like asking what's north of the North Pole. The question breaks down because it assumes a larger framework in which the universe is embedded. But if the universe is everything, all of space and time, then there is no outside. The universe isn't sitting in a box or surrounded by empty space. It is space. Now, it's important to be careful with the analogy. The surface of a balloon is 2-dimensional, and it's expanding in a 3rd dimension, outward into the air around it. That's just a limitation of the model. In the real universe, we don't have any evidence that our 3-dimensional space is embedded in a higher dimensional space. The universe could be curved without needing an outside dimension to do the curving. That's something geometry allows. What matters is the internal geometry, how distances behave within the universe. In the balloon model, the two-dimensional creatures living on the surface wouldn't know about the third dimension. They would only be able to measure how far apart things are on the surface. From their perspective, the surface could be curved and distances could increase without any need for an external space. In cosmology, this kind of curvature is described using general relativity, the theory that describes how space and time are shaped by matter and energy. According to general relativity, space can curve in on itself, depending on the total amount of mass energy. The more mass and energy present, the more space curves. This is what leads to the different possibilities: positively curved, negatively curved, or flat. In the balloon analogy, the curvature is positive, like a sphere. This corresponds to a universe that is finite but unbounded. In such a universe, you could travel in one direction forever and return to where you started, without ever encountering an edge. The balloon shows how such a shape can exist and expand at the same time. Another important part of the analogy is how it explains the redshift of light. As the universe expands, the light traveling through space gets stretched out. This means its wavelength increases, shifting it toward the red end of the spectrum. This redshift is one of the main observations that supports the idea of an expanding universe. The farther away a galaxy is, the more its light is redshifted, because the space between us and the galaxy has expanded while the light was on its way. The balloon model helps visualize this. Imagine drawing a wave, like a squiggly line, on the surface of a balloon. As the balloon expands, that wave stretches. The peaks and valleys get farther apart. This is what happens to light in an expanding universe. Its wavelength increases as space itself grows. It's also worth noting what the balloon analogy doesn't show. It doesn't include gravity, dark energy, or the effects of mass on local space. It's a large-scale, simplified picture, good for illustrating cosmic expansion, but not for everything. Still, as a conceptual tool, it helps make the idea of an expanding, possibly finite universe easier to grasp. There's also the question of what happens over time. In the balloon analogy, as the balloon keeps inflating, the dots on the surface move farther apart at an increasing rate. In our universe, observations show that the expansion is accelerating. Galaxies are moving away from each other faster over time. This is believed to be caused by dark energy, a form of energy that fills space and drives the acceleration. While dark energy isn't part of the balloon model, the overall idea of increasing separation still applies. The key takeaway from the balloon analogy is that space can expand without requiring an edge. The universe can grow without growing into anything, and it can be finite in volume without having a boundary. These ideas are difficult to picture directly because we live in a world where most things have borders, shapes, and containers. But the universe as a whole might not follow those rules. The balloon also shows why the universe has no center. There is no special dot on the balloon's surface that all others are moving away from. Every point on the surface sees all other points moving away. This is what cosmologists mean when they say the universe has no center and no edge. It's expanding uniformly in all directions from every point. That's consistent with the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales, meaning it looks the same everywhere and in every direction. If you were to place yourself anywhere in the universe and look around, you'd see galaxies receding from you in every direction. That's not because you're at the center, but because space itself is expanding uniformly. Just like a dot on the surface of a balloon sees all other dots moving away, you would too, no matter where you were. This is one of the harder ideas to accept, because it's so different from our everyday experience. But it's what the evidence supports. The balloon analogy doesn't explain everything, but it captures the essence of cosmic expansion, curved space, and a universe without edges. Ultimately, models like the balloon analogy help bridge the gap between advanced mathematics and everyday understanding. They simplify complex ideas just enough to make them accessible, without being too inaccurate. For many people, this analogy is the first step toward seeing the universe not as an object in space, but as space itself, something dynamic, flexible, and capable of expanding without needing more room. So when we ask if space ends, it's worth remembering that expansion doesn't mean expansion into something else. The balloon doesn't grow into the room around it, from the perspective of the surface. It just stretches. And so might the universe, not growing outward, but growing everywhere at once. When thinking about the universe, one question often comes up. Does it have an edge? The idea makes intuitive sense. Most things we interact with have limits. A field ends at a fence. A road stops at an intersection. A book has a last page. So, when we look up at the stars, it's natural to ask, where does it all stop? To answer that, we need to clarify what we mean by edge. Do we mean a physical border, like a wall? A place where space itself ends? Or do we mean the farthest point we can observe? These are different questions, and each has a different answer depending on how we define space and how we measure it. One way to think about the universe is by considering the observable universe. This is the region of space we can see from Earth. Light takes time to travel, so when we look at distant galaxies, we're seeing them as they were in the past. The most distant light we can detect has traveled for about 13.8 billion years, the age of the universe. But because the universe has been expanding during that time, those galaxies are now much farther away than 13.8 billion light years. Current estimates place the radius of the observable universe at about 46 billion light years in every direction. That makes the observable universe a sphere about 93 billion light years across. But this observable region is not the whole universe. It's just the part from which light has had time to reach us since the beginning of cosmic time. There could be much more space beyond it. We simply can't see it yet, because its light is still on the way. This leads to a key point. The edge of the observable universe is not an edge of space itself. It's the limit of what we can observe, not the end of what exists. Space may continue far beyond what we can see, possibly infinitely. Or it may loop back on itself, meaning you could keep traveling and eventually return to your starting point. Either way, there's no evidence of a hard boundary. There's also no sign of a wall or surface marking the edge of space. In all directions, galaxies are distributed smoothly. There's no thinning out or sudden drop. The density of galaxies fades gradually due to the expansion of space and the limits of light travel, but it doesn't abruptly end. The notion of a cosmic edge runs into problems when we try to define what would be beyond it. If the universe had a boundary, what would be on the other side? More space? Nothingness? Another universe? These are hard questions to frame scientifically because we have no evidence of such a boundary or anything beyond it. In physics, we generally avoid introducing concepts that can't be observed, measured, or modeled. Since there is no data suggesting a physical edge, most cosmological models don't include one. Instead, the geometry of the universe provides a better way to understand this. If the universe is curved like the surface of a sphere, it can be finite in size, but have no edge. You could travel around it forever without encountering a border. This is known as being finite, but unbounded. It's like walking around the surface of the earth. You never fall off, but you can come full circle. Alternatively, the universe could be flat and infinite. This is consistent with current measurements of the cosmic microwave background radiation and the distribution of galaxies. A flat, infinite universe has no edges either, just endless continuation in all directions. In this model, asking where space ends is like asking where the number line stops. It doesn't. Some people imagine the universe as an object floating in a larger space, like a ball sitting in a box. But this idea assumes there's something for it to sit inside. According to general relativity, space isn't a thing inside something else. It is the framework itself. It's not expanding into a larger space. It's just expanding. Every point in space is moving away from every other point as the universe grows. There's no center, and there's no outer shell. Even if we tried to define an edge as the place where there is no more matter or radiation, that also doesn't work. Space isn't empty in the sense of being nothing. It has properties. It can stretch, curve, and carry energy. And quantum physics tells us that even in a vacuum, particles flicker in and out of existence. There's no clear line between something and nothing. When cosmologists use simulations and mathematical models to study the universe, they consider various possibilities for its shape and size. Some models allow for compact, finite universes. Others allow for infinite ones. But none of them include a hard edge where things simply stop. That concept doesn't appear in the math or the observations. The Big Bang is often misunderstood as an explosion from a point outward into space. But that's not what it was. The Big Bang happened everywhere at once. It was the beginning of space and time, not an event inside space. Every point in the universe today was compressed into a smaller state. The expansion isn't from a location. It's a change in the scale of space itself. If there had been an edge at the beginning, it would have left a signature in the cosmic microwave background or in the structure of galaxy formation. We don't see that. Instead, the universe appears remarkably uniform and isotropic on large scales. That means it looks the same in all directions and from all locations. Another question sometimes asked is whether we could ever reach the edge of the universe by traveling far enough. But even if the universe is finite, you would never encounter a wall. If it loops back on itself, you'd just keep going. And if it's infinite, you could travel forever and never run out of space. The expansion of the universe complicates things further. As space grows, distant galaxies move away from us faster. Eventually, some will recede faster than the speed of light, not because they're moving through space quickly, but because the space between us is expanding. This means that over time, more and more of the universe will become unobservable. But again, this isn't due to an edge. It's due to the dynamics of space-time. Even if you could travel at the speed of light, you'd still be limited to what lies within the observable universe. You'd never reach a boundary because space itself would keep stretching in front of you. The farther you go, the more space there is, and the more time it would take to reach anything else. In a way, the edge keeps moving. Some speculative models, like those involving a multiverse, propose that our universe is one region inside a larger framework. But even in these models, individual universes don't necessarily have edges. They may bud off from each other like bubbles in foam, or they may form as fluctuations in a larger field. These ideas are not yet supported by direct evidence, but they show how the idea of an edge is avoided even in more exotic theories. Philosophically, the idea of an edge implies a separation between what is and what is not. But space-time, as understood in physics, doesn't require this kind of separation. Space doesn't have to end just because we're used to objects having limits. The universe isn't an object in space. It is space. Ultimately, the question of an edge touches on the nature of the universe itself. Is it finite or infinite? Does it have a shape that curves back on itself, or does it go on forever? So far, the evidence points to a universe that has no boundary, no center, and no outer edge. Space may continue without end, or it may be bounded in a way that never leads to a wall. In either case, the concept of an edge does not appear in our best understanding of cosmology. That doesn't mean the question isn't meaningful. It's a natural one, and it reflects our desire to find structure in the vast unknown. But in this case, the structure we find is not a wall, a shell, or a boundary. It's a set of physical laws and observations that suggest the universe is larger and stranger than our everyday experience prepares us for. So, when we look into the sky and ask whether there's an edge to space, the best answer we can give, based on current science, is no. There's no outer limit, no end wall, no cosmic fence, just more space, expanding, evolving, and perhaps continuing forever. The universe is getting bigger. That idea has become part of how we understand space today. But what does it really mean for the universe to expand? It's not a simple question. Unlike a balloon or a cloud growing in size, the expansion of the universe doesn't involve objects moving through space. It involves space itself stretching, changing the distances between things without requiring them to move through it. The discovery of this expansion began in the early 20th century. In 1929, astronomer Edwin Hubble measured the light coming from distant galaxies and found that it was redshifted. This means that the light's wavelength had been stretched toward the red end of the spectrum. The farther away a galaxy was, the greater its redshift. That pattern was consistent across the sky. Hubble's observation led to a remarkable conclusion. The farther a galaxy is from us, the faster it appears to be moving away. This relationship became known as Hubble's law. It suggested that the universe was expanding in all directions. But the expansion wasn't due to galaxies flying outward like debris from an explosion. Instead, the space between them was growing. The galaxies weren't pushing into new territory. The territory itself was enlarging. This is the key difference between the universe expanding and objects moving within a fixed space. In the case of cosmic expansion, galaxies remain relatively stationary in space. It is the grid of space itself, the underlying fabric, that stretches. As it stretches, Everything embedded in it, such as galaxies and clusters of galaxies, moves farther apart. You can think of it like points on a rubber sheet. If the sheet is marked with dots and then stretched evenly, the dots move farther apart, even though they're not moving themselves. The sheet grows, and the space between the dots increases. This is roughly how the expansion of space works. On a large enough scale, the distances between galaxies increase as space itself grows. It's important to understand that this expansion doesn't affect everything equally. It only applies on the largest cosmic scales. Within galaxies, stars and planets remain bound together by gravity. The same is true for solar systems and atoms. The expansion of space is extremely weak on small scales, and it's easily overpowered by other forces. That's why we don't feel the universe stretching around us. The Earth doesn't move away from the Sun, and your house doesn't get bigger over time. Instead, the expansion is visible only when we look at vast distances between galaxies that are not gravitationally bound to each other. These large-scale structures drift apart, not because they're pushing away from each other, but because the space between them is increasing. This is a key point. It's not motion through space, it's motion with space. The concept of expanding space comes from general relativity, Albert Einstein's theory of gravity. In this framework, gravity is not a force acting at a distance, but the result of mass and energy curving space and time. The equations of general relativity allow for dynamic solutions, universes that change in size and shape over time. In the 1920s, a mathematician named Alexander Friedmann used Einstein's equations to show that the universe could be expanding or contracting. Around the same time, Georges Lemaitre, a Belgian priest and physicist, independently came to a similar conclusion. He even proposed that the universe began from a single, dense point, a concept that would later evolve into the Big Bang theory. These models showed that the fabric of space could evolve. If you imagine a grid of space, each line stretching over time, the distances between points grow. This stretching of space causes the wavelengths of light to stretch as well. That's why distant galaxies appear redshifted. Their light has been stretched as space expanded during its journey to us. The rate at which the universe expands is described by the Hubble constant. It tells us how fast galaxies appear to recede per unit of distance. For example, if the Hubble constant is about 70 kilometers per second per megaparsec, then a galaxy 1 megaparsec away will appear to be moving away at 70 kilometers per second. A galaxy 2 megaparsecs away will appear to recede at 140 kilometers per second, and so on. However, the expansion rate has not always been constant. Observations suggest that the early universe expanded rapidly, then slowed down due to the pull of gravity. But more recently, the expansion has started to speed up again. This surprising acceleration was discovered in the late 1990s by studying supernovae in distant galaxies. The cause of this acceleration is not fully understood, but it has been attributed to a mysterious component called dark energy. Dark energy is thought to make up about 70% of the total energy content of the universe. Unlike matter or radiation, dark energy doesn't clump or dilute as the universe expands. It exerts a repulsive effect, driving space to stretch faster and faster. This means that the universe isn't just getting bigger, it's getting bigger at an accelerating rate. Galaxies that are far enough away will eventually be moving away from us faster than the speed of light, not because they're breaking any cosmic speed limit, but because the space between us and them is growing that fast. In general relativity, this is allowed. The speed of light limit only applies to motion through space, not to the expansion of space itself. As the universe continues to expand, more and more of it will become unreachable. Light from distant galaxies will never have a chance to reach us, because the space between us and them will be stretching faster than the light can travel. This leads to a future where only our local group of galaxies remains visible. The rest of the universe will fade away beyond the cosmic horizon. The cosmic horizon is the limit of what we can ever observe, even with perfect instruments and infinite patience. It's not a physical wall, but a boundary set by the speed of light and the expansion of space. As space grows, the horizon shrinks in a relative sense. Fewer things remain within reach. Understanding the expansion also helps explain the age and history of the universe. If we run the expansion backward in time, we arrive at a moment when the universe was extremely hot and dense. This is the starting point of the Big Bang model. Not an explosion in space, but the rapid expansion of space itself from a very compact state. From this initial condition, space began to stretch. Matter cooled and spread out. Galaxies formed. Over billions of years, the structures we see today emerged. The expansion has continued throughout this entire history, shaping the large-scale structure of the cosmos. There are still open questions about the nature of expansion. For example, is it truly infinite? Will it continue forever? Will it slow down again? Or could it reverse? These depend on the exact properties of dark energy and the total energy density of the universe. So far, observations suggest a flat geometry and an accelerating expansion, pointing to a future where space continues to grow without end. It's also important to note that expansion does not affect the shape or motion of individual galaxies in a direct way. Galaxies are held together by gravity, and their stars orbit the galactic center as usual. It's the large voids and filaments between galaxy clusters that feel the expansion most directly. These vast regions are where space itself stretches most clearly. In practical terms, this expansion has no effect on daily life. It's not something we notice. But in cosmological terms, it defines the structure and fate of everything. It sets the scale for all observations, determines how light travels, and influences how we understand time and distance on the largest scales. In summary, the expansion of the universe is not like an explosion or a spreading cloud. It's a stretching of space itself. Galaxies move apart because the space between them increases. This expansion has been going on since the beginning of cosmic time, and it continues today, faster than ever. It is one of the fundamental features of our universe, shaping both what we see and what we can never reach. When we look up at the night sky, we see light that has traveled across immense distances. Some of it comes from nearby stars, others from far-off galaxies. But no matter how powerful our telescopes become, there is a limit to how far we can see. That limit is set by the age of the universe and the speed of light. This boundary defines what's known as the observable universe. It includes everything we can, in principle, observe from Earth. But beyond that lies the actual universe, potentially far larger, perhaps even infinite. Understanding the difference between these two is essential for grasping our true place in the cosmos. The observable universe is a sphere centered on the observer, in our case, Earth. Its radius is not simply the age of the universe multiplied by the speed of light, even though that would seem intuitive. Instead, it's affected by the fact that space itself has been expanding during the entire history of the universe. Because of this expansion, the most distant objects we can see now were much closer when they emitted the light we're just receiving. While the light has traveled for about 13.8 billion years, those sources are now over 46 billion light-years away. That makes the observable universe roughly 93 billion light-years across. The key idea is that this observable boundary is not a physical edge in space. It's a limit in time and light. It marks the most distant regions from which light has had time to reach us since the beginning of the universe. Beyond it, there may be countless galaxies, clusters, and structures we will never see, not because they don't exist, but because their light hasn't had enough time to arrive. The actual universe includes everything beyond that boundary. If space is infinite, then the actual universe extends forever, well past what we can observe. If space is finite but unbounded, like the surface of a sphere, then the actual universe still wraps around on itself and may contain vastly more than we can detect. In both cases, the observable universe is just a small piece of the whole. It's worth noting that the observable universe is different for every observer. A galaxy located billions of light-years away has its own observable universe, centered on itself. Our observable spheres overlap, but they are not identical. Each observer can only see a portion of the universe limited by their position in space and the time since light began traveling. When astronomers look deep into the sky, they are essentially looking back in time. Because light takes time to travel, distant objects appear as they were in the past. A galaxy, 10 billion light-years away, is seen not as it is now, but as it was 10 billion years ago. The edge of the observable universe marks the earliest possible light we can detect, the cosmic microwave background. This radiation was released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and space became transparent to light. Before that time, the universe was opaque. Even though we can't see past the cosmic microwave background directly, we can infer what came before it using theoretical models and indirect measurements. Particle physics and cosmology together describe what the early universe was like during its first seconds and even fractions of a second. These models suggest the universe was once much smaller, hotter, and denser, and it has expanded and cooled over time. As the universe expands, more distant regions become unreachable. Some galaxies are already so far away that the light they emit today will never reach us, not even in the future, because space between us is expanding faster than the speed of light. This isn't a violation of physics. The speed of light limit only applies to objects moving through space, not to the expansion of space itself. As a result, there's a growing part of the universe that's permanently beyond our reach. This has consequences for what we can know. Observations are confined to the light that arrives here. We build our understanding of the universe based on this limited data. Even so, the observable universe contains hundreds of billions of galaxies, each with billions of stars. Within just this portion of space, the scale is already vast beyond everyday comprehension. Scientists make educated guesses about what lies beyond the observable boundary. The assumption, based on the cosmological principle, is that the universe is roughly the same everywhere on large scales. That means the parts we can't see are probably similar in structure and composition to the parts we can. This principle is supported by the remarkable uniformity of the cosmic microwave background and the distribution of galaxies in all directions. Still, we can't confirm what lies beyond the observable horizon. There could be regions with different physical constants, different structures, or even no galaxies at all. These ideas are purely speculative. Some theoretical models, such as those involving inflation or the multiverse, suggest that different regions might have different properties, but these remain unproven. Inflation is one idea that plays a key role in understanding the size of the actual universe. According to this theory, during a very brief period after the Big Bang, less than a trillionth of a second, the universe underwent a rapid exponential expansion. In that instant, tiny quantum fluctuations were stretched across cosmic scales, seeding the formation of galaxies. Inflation explains the uniformity of the observable universe and its flat geometry. But it also implies that space is much larger than we can observe, possibly infinite. If inflation occurred, then what we see is just a tiny patch in an unimaginably vast structure. Despite these possibilities, our data comes only from the observable portion. That's where telescopes, satellites, and experiments gather their measurements. These observations shape our understanding of the universe's age, composition, and geometry. They show that the universe is expanding, that it's filled with dark matter and dark energy, and that it likely began in a hot, dense state. Dark matter and dark energy are components we can't see directly, but their effects are visible. Dark matter influences the motion of galaxies and the formation of large-scale structures. Dark energy drives the acceleration of cosmic expansion. Both play a crucial role in shaping what we observe, and both are part of the actual universe, even though much of their influence lies beyond our observational reach. As time passes, the observable universe changes. It grows as more light has time to reach us, but it also shrinks in a relative sense because some regions are moving away faster than light can travel. In the very distant future, only a few nearby galaxies will remain visible. Most of the universe will disappear beyond the horizon, not because it ends, but because we'll never see it again. There's also the possibility that some parts of the universe will always remain hidden, not just temporarily, but permanently. Some light may never reach us because it was emitted too far away, or because space expanded too quickly after it was released. This light is lost to us, unless the expansion of space somehow slows down, which current observations suggest is unlikely. Cosmology continues to refine measurements of the observable universe. Tools like the Hubble Space Telescope, the James Webb Space Telescope, and cosmic microwave background missions like Planck provide better maps of the early universe. They help estimate the age of the universe, the rate of expansion, and the distribution of matter. These measurements confirm that the universe appears flat on large scales, and that it's isotropic and homogeneous. But they also show the limits of our observation, how much lies beyond our reach. Despite this limit, The observable universe contains a complete record of cosmic history. Every photon of light carries information about the conditions when it was emitted. By collecting this light, scientists reconstruct the evolution of the universe from its first few seconds to the present. Even if we never see the full size of the actual universe, we can learn a great deal from the light we do receive. This separation between the observable and the actual reminds us that knowledge always comes with boundaries. What we see is not necessarily all there is. Yet the consistency of what we observe gives us confidence in our models. Even though the true size and shape of the universe remain uncertain, the part we can study gives us a coherent and detailed picture of how the cosmos works. And so, when we look up at the stars, we are seeing only part of a much larger whole. The observable universe is a window into the past and a guide to what might lie beyond. It defines the limits of what we can see, but it also points to the possibility of more galaxies, more space, and more time, stretching far beyond the edge of visibility. The universe has a horizon, not one made of mountains or clouds, but of light. It's not visible to the eye, but it marks the outer boundary of what we can ever know. This limit is known as the cosmic horizon. It defines the farthest points from which light has had enough time to reach us since the beginning of the universe. It's not a physical wall or an edge in space. It's a consequence of time, distance, and the speed of light in a universe that has been expanding for billions of years. To understand the cosmic horizon, it helps to begin with how light works across large distances. Light travels fast, about 300,000 kilometers per second, but not infinitely fast. It takes time for it to cross space. When we look at the moon, we see it as it was about 1 second ago. The sun appears as it was 8 minutes ago. Light from the nearest star system, Alpha Centauri, takes over 4 years to reach us. And when we look at distant galaxies, we're seeing light that's been traveling for millions or even billions of years. This delay means that our view of the universe is also a view into its past. The farther away we look, the further back in time we see. But there's a limit. The universe is about 13.8 billion years old. So, the furthest light we can possibly receive is light that's been traveling for no more than 13.8 billion years. This sets a basic limit on how far we can see, assuming the universe has been expanding at a steady rate. But space hasn't expanded steadily. It's been stretching, and the rate of expansion has changed over time. Early on, the expansion was rapid, then it slowed, and now it's speeding up again due to dark energy. Because of this, the actual distance to the most distant objects we can observe isn't 13.8 billion light years. It's more, much more. The light has been traveling toward us for 13.8 billion years, but the source of that light has moved farther away during that time. Due to this expansion, the current distance to the most distant light we can detect is about 46 billion light years in every direction. That 46 billion light year radius defines our cosmic horizon. It's the limit of our observational reach. Beyond it, light hasn't had time to reach us since the beginning of the universe. Those regions of space may exist, but they are invisible to us now and may remain so forever. This horizon is different from the observable universe's edge in a subtle but important way. The observable universe is defined by how far light has traveled to reach us. The cosmic horizon, on the other hand, includes how far away those sources are today, after accounting for the expansion of space. In other words, light that started its journey billions of years ago is only just arriving now, but the place it came from has moved much farther away than when it first emitted that light. There's another type of cosmic horizon called the event horizon, which is more strict. It marks the limit beyond which events can never affect us, not even in the infinite future. This arises because of the accelerating expansion of the universe. Some galaxies are receding from us faster than the speed of light, not because they're moving through space quickly, but because space itself is stretching between us. In an accelerating universe, the number of galaxies we can see today will shrink over time. Eventually, many will cross the event horizon, meaning their light will never reach us again, no matter how long we wait. This is not a theoretical curiosity. It has real consequences for how the future of the universe will unfold. Right now, we can see billions of galaxies, but in the distant future, we'll see fewer and fewer. The accelerating expansion means that galaxies currently near the edge of visibility will eventually disappear from view. Their light will never reach us again because the space between us will be expanding faster than light can travel. That doesn't mean those galaxies vanish or cease to exist. They will continue to evolve, form stars, and go through their own cosmic history. But from our perspective, they'll be lost to time. The cosmic horizon creates a limit not just to what we see today, but to what we can ever interact with. It's a moving boundary shaped by the expansion rate and the passage of time. If we think of the universe as a map, the cosmic horizon draws a circle around us. It's not a fixed circle. It's dynamic, always shifting depending on the rate of expansion and the age of the universe. In a universe without acceleration, this horizon would grow over time, allowing us to see more and more distant objects. But because the expansion is speeding up, we are losing sight of more than we are gaining. Even now, some galaxies are already beyond the event horizon. We can still see the light they emitted in the past, but we'll never see anything newer from them. The last photons they sent toward us are already on their way, and once they arrive, no further information will come. These galaxies are, for practical purposes, becoming permanently silent. This has deep implications. In the far future, perhaps tens or hundreds of billions of years from now, the only galaxies still visible will be those bound to our own. Everything else will have faded from view. Future astronomers might not know about the Big Bang, cosmic expansion, or the large-scale structure of the universe, simply because they'll no longer be able to see it. Their sky could look far emptier than ours does today. The cosmic horizon doesn't only affect what we see. It defines the boundary of what we can measure, test, and know through observation. Everything beyond that horizon is, by definition, beyond confirmation. We may build models about what lies beyond it, but we can't directly observe those regions. This doesn't mean science stops at the horizon, but it does mean that certainty fades as we cross it. The horizon also helps define our place in space-time. It reminds us that we are not seeing the universe as it is now, but as it was. Every part of the sky is a window into a different moment in history. The farther we look, the younger the universe was at that time. The cosmic microwave background, the oldest light we can see, shows the universe just 380,000 years after the Big Bang. It forms a sort of inner surface to the cosmic horizon, a limit in time as well as distance. Technological advances can't change this limit. We can build better telescopes and collect fainter light, but we can't receive information that simply hasn't arrived. Even with perfect instruments, the cosmic horizon stands as a firm boundary. It's not a technological limit. It's a physical one, built into the structure of space and time. What lies beyond the cosmic horizon? Possibly more galaxies, more structure, and more space. If the universe is infinite, the regions beyond our horizon are just more of the same. If it's finite but large, we may never know its full extent. Some models of inflation suggest that the universe is vastly larger than what we can see, perhaps many times the size of the observable portion. Others propose a multiverse, where different regions of space have different physical properties. But these ideas remain speculative because they're beyond our observational reach. The cosmic horizon is not a wall or a boundary in the usual sense. It doesn't stop particles or block objects. It simply marks a limit on communication. Beyond it, light hasn't had enough time to reach us, and in some cases, never will. It's an invisible line drawn not by matter, but by the interaction of light, space, and time. Over time, this horizon defines the visible universe and limits the data we can collect. But within that boundary, we have discovered a remarkable amount. We know about galaxies billions of light years away. We've mapped the afterglow of the Big Bang. We've studied how space stretches and curves, and we continue to learn more even as the horizon slowly closes in. In a sense, the cosmic horizon is a reminder of both the richness of the universe and the limits of our perspective. It tells us that there is more out there than we can ever see, and that our window onto the cosmos is shaped by the nature of reality itself. We don't live at the center of the universe, but we do live at the center of our observable horizon, a sphere defined not by space, but by time and light. That sphere is vast, nearly 93 billion light-years across, and yet it's only a fraction of what's out there. As we observe the universe from within that bubble, we are always looking outward in time, tracing the history of cosmic expansion and the flow of energy through space. In the end, the cosmic horizon stands not as a barrier, but as a marker. It shows us how far we've come in understanding the universe, and how much still lies beyond our reach. When we look out into the cosmos, the vastness is difficult to grasp. Billions of galaxies, each with billions of stars, spread across space as far as telescopes can see. But however far we look, there's always more. Another galaxy, another cluster, another faint glow on the edge of visibility. That naturally leads to a deeper question. Is space infinite? Does it go on forever? Or is it somehow finite, with a size that could be measured if only we could see it all? The truth is, science doesn't yet have a definite answer. What we can say with confidence is that the universe appears flat, homogeneous, and isotropic on the largest scales. This observation comes primarily from measurements of the cosmic microwave background radiation, the leftover light from the early universe. Its patterns and temperature fluctuations suggest that space is flat within a small margin of error. But this still leaves open two possibilities. Space could be infinite, or it could be finite but unbounded. To understand these two options, it helps to consider how geometry works on large scales. A flat universe means that, on average, the rules of Euclidean geometry apply. Parallel lines stay parallel. Triangles have angles that add up to 180 degrees, and the shortest distance between 2 points is a straight line. A curved universe, by contrast, would show deviations from these properties. A positively curved universe, like the surface of a sphere, would have angles in a triangle adding to more than 180 degrees. A negatively curved one, like a saddle, would have angles adding to less. Observations so far suggest the curvature is extremely close to zero. If the universe is curved, it is curved so gently that the observable part looks flat. That alone doesn't prove it's infinite. It could be a very large sphere, too big for us to notice the curvature. But flatness is consistent with infinite extension, and many cosmological models assume an infinite universe because it's mathematically simpler and fits the data. Still, flatness alone isn't the whole story. To understand whether the universe is infinite, we also have to consider its topology, the way space is connected. Even a flat space can be finite if it loops back on itself. Think of a video game screen where exiting one edge brings you back on the other side. This is called a toroidal topology. In such a universe, traveling far enough in one direction could bring you back to your starting point. You'd never find an edge, but space would be finite. Detecting such a structure is challenging. One approach is to look for repeating patterns in the cosmic microwave background. If light has had time to wrap around the universe, we might see the same pattern in different directions, like looking into a room with mirrors on all sides. So far, no such patterns have been observed, but the absence of evidence doesn't rule out the possibility. It may be that the universe is simply too large for light to have made a full circuit since the Big Bang. If the universe is infinite, then its implications are profound. An infinite universe means that there's no center and no edge. Every point in space would be surrounded by an infinite expanse in all directions. No matter how far you travel, you would never reach a boundary. This raises difficult questions about energy, matter, and structure. Can an infinite universe contain an infinite amount of matter? How do we reconcile that with conservation laws? Does everything repeat eventually if space goes on forever? These are deep questions, and some can be addressed through statistical reasoning. Even in an infinite universe, the observable portion, the part we can see, is finite. That means we only interact with a finite sample of what exists. The laws of physics as we understand them may apply uniformly, but we have no way to verify that beyond our observational horizon. Another implication of infinity is that every possible configuration of matter within the limits of physics could occur somewhere. If the universe is truly infinite, then every arrangement of atoms, including one that looks just like Earth or just like you, could exist an infinite number of times. This is not science fiction. It follows directly from combining infinite space with finite combinations of matter. However, these ideas drift away from what we can test or observe. Science becomes limited to probabilities and models, rather than direct confirmation. A finite universe, on the other hand, avoids these issues. It contains a finite amount of matter and energy, with a structure that can, in principle, be fully described. But a finite universe does not mean it has an edge. Just like the surface of a sphere, a finite space can be unbounded. It closes in on itself in all directions. You could travel forever without ever reaching an end, but you'd eventually return to your starting point. Finite, yet endless in experience. What determines whether the universe is finite or infinite is a combination of its geometry, expansion history, and initial conditions. The early universe underwent a phase called inflation, where space expanded exponentially fast for a brief moment. Inflation smooths out irregularities and drives curvature toward zero. If inflation lasted long enough, it would have stretched the universe so much that any curvature or boundary became unobservable. In this case, even a finite universe could appear flat and infinite to us. Some versions of inflation suggest that it never ends entirely, that it keeps going in parts of space while stopping in others. This leads to the idea of a multiverse, where our observable universe is just one bubble in a vast, possibly infinite foam of universes. Each bubble might have different physical laws. But this concept is far beyond what we can currently observe or measure. So while it's an interesting idea, it's not needed to answer the basic question of whether our space is infinite. One of the challenges with infinite models is that they push the boundaries of what can be tested. Science depends on evidence. If something lies beyond the reach of any experiment or observation, it becomes difficult to support with certainty. That's why many cosmologists focus on what we can observe. The observable universe is about 93 billion light-years in diameter. Whether space continues beyond that in all directions is still unknown. The limits of observation also mean that we may never be able to tell the difference between a truly infinite universe and a very large finite one. If space is 100 times larger than the observable universe, it would still appear flat and endless from our point of view. There would be no practical difference between extremely large and truly infinite, at least in terms of what we can detect. Ultimately, the question of whether space is infinite may not have a definitive answer. It may depend on how the universe began, whether it had a boundary condition, and how inflation played out in its earliest moments. These are active areas of research, combining cosmology, quantum theory, and general relativity. New measurements, such as those from space telescopes and experiments on the cosmic microwave background, may help refine our models. But even with perfect data, we may always be limited by the horizon of what light can show us. Even so, thinking about the size of space helps put things in perspective. Whether space is infinite or not, it is enormously larger than our everyday experience. The distances between stars, the scale of galaxies, the structure of cosmic filaments, these stretch across millions of light years. In that context, the Earth is a tiny point, and even our galaxy is just a dot. Despite our small place in the cosmos, we have developed tools and models to explore its structure. Through careful measurement of redshift, background radiation, and gravitational behavior, scientists have been able to infer the curvature and topology of space. These techniques don't yet give a final answer, but they build a consistent picture of a universe that is either infinite or so vast that the difference doesn't affect what we can observe. In everyday life, the question of whether space is infinite has no practical effect. But in physics and cosmology, it shapes how we understand time, distance, and the structure of reality. It touches on deep concepts: how something can have no edge, how geometry influences motion, and whether the universe has a boundary or just goes on forever. So is space infinite? Maybe, Current data allows for it. It also allows for a finite universe that appears infinite from within. The evidence we have doesn't rule either out. The cosmos might extend forever, or it might fold back on itself in ways we can't yet detect. For now, all we can do is measure what we see, test our models, and recognize the scale of what lies beyond. And whether it ends or not, space continues to challenge our understanding, with its vastness, its silence, and its still unanswered questions. When we imagine space, it's easy to think of it as flat, like a sheet of paper extending endlessly in all directions. Most of our everyday experiences follow the rules of flat geometry. On a table, two straight lines that start off parallel will stay parallel. Triangles have angles that always add up to 180 degrees. And distances can be measured with rulers that work the same everywhere. But the universe doesn't necessarily obey these rules on large scales. Its shape may be different from what we intuitively imagine. In fact, space itself can be curved, gently, imperceptibly, but significantly over billions of light years. The concept of curvature in space comes from general relativity. Einstein's theory describes gravity not as a force, but as the result of mass and energy bending the fabric of space and time. In the presence of matter, space curves. Objects follow the straightest possible paths through this curved space, which to us appear as orbits or falling motions. While this curvature is strongest near massive bodies like stars or black holes, general relativity also applies to the universe as a whole. The average curvature of the entire universe, its global geometry, is a key aspect of cosmology. There are three basic possibilities. Space can be positively curved, negatively curved, or flat. Positive curvature means that space bends inward, like the surface of a sphere. In such a universe, the geometry changes. Triangles have angles that add up to more than 180 degrees, and straight lines eventually converge. If you traveled far enough in a straight line, you could end up back where you started, without ever encountering an edge. This kind of space is finite, but unbounded. Negative curvature is the opposite. Space bends outward, like a saddle. In this case, triangles have angles that add up to less than 180 degrees, and parallel lines eventually diverge. Such a universe would be infinite, with a distinctive structure where the geometry of large-scale space looks very different from the flat kind we're used to. Flat space, on the other hand, follows the rules of Euclidean geometry. Triangles behave as expected, and parallel lines stay parallel. This doesn't mean the universe is literally a flat sheet. It still has three spatial dimensions, but it means the curvature is zero on average. Flatness is the dividing line between the other two possibilities. It represents a balance in the total energy content of the universe. Determining the curvature of the universe requires careful measurement. One of the most powerful tools for this task is the cosmic microwave background, the afterglow of the Big Bang. This faint radiation fills all of space and carries a snapshot of the universe when it was just 380,000 years old. Tiny variations in its temperature reflect sound waves that moved through the hot, dense early universe. By analyzing the size of these temperature fluctuations on the sky, scientists can infer the geometry of the space the light has traveled through. The logic is straightforward. If space is flat, the fluctuations will appear at a specific angular size. If space is positively curved, the same fluctuations will appear larger, as if magnified. If space is negatively curved, they'll appear smaller, as if the light paths have diverged. Measurements from satellites like WMAP and Planck have found that the fluctuations match what's expected in a flat universe, with only tiny deviations allowed. The margin of error is small, about 0.4%, which means if the universe is curved, the curvature is extremely slight. This result strongly supports the idea that the universe is flat on large scales, but it doesn't prove the universe is infinite. A finite universe can still be flat if it has a specific kind of topology, like a three-dimensional torus. In this model, space loops back on itself in all directions, much like in certain video games. Light could, in principle, travel around such a universe and return to its starting point, though this would take longer than the current age of the universe. So even a flat universe might still be finite. Another line of evidence comes from large-scale surveys of galaxies. By mapping the distribution of galaxies across the sky, astronomers can look for patterns that would indicate large-scale curvature. These surveys also support flatness, though again, only within the observable universe. Beyond that, we can't see, and curvature on larger scales remains unknown. The shape of the universe is closely tied to its overall density. In cosmology, this is often described using a quantity called the critical density. If the actual density of matter and energy in the universe equals the critical density, the universe is flat. If it's greater, the universe is positively curved. If it's less, the universe is negatively curved. The ratio of the actual density to the critical density is known as the density parameter, often written as omega, O. Observations suggest that O is very close to 1, indicating flatness. The different types of curvature also affect the fate of the universe. In the past, cosmologists believed that a positively curved universe would eventually stop expanding and begin to contract, leading to a big crunch. A negatively curved universe would expand forever, but at a decelerating rate. A flat universe would expand forever too, but at the slowest possible rate. However, these predictions have changed with the discovery of dark energy. Dark energy is a mysterious component of the universe that causes space to expand at an accelerating rate. It was discovered in the late 1990s by observing distant supernovae, which appeared dimmer than expected. This acceleration means that the geometry of space alone no longer determines the ultimate fate of the universe. Even a positively curved universe could expand forever if dark energy dominates. As it stands, current models include dark energy as part of the total energy budget of the universe, and the flatness result includes it. The presence of dark energy has shifted the focus of cosmology. While curvature still matters, the evolution of the universe now depends more on the properties of dark energy, how strong it is, whether it changes over time, and what its true nature is. But measuring the curvature still tells us about the early universe and the conditions that led to what we see today. The flatness of the universe also provides support for the theory of cosmic inflation. According to this idea, the universe underwent a brief but dramatic expansion in the first fraction of a second after the Big Bang. During this time, space stretched by a factor of at least 10^26 in a tiny instant. This enormous expansion would smooth out any initial curvature, making the universe appear flat even if it started out curved. Inflation predicts a flat universe, and the observed flatness fits well with this prediction. Despite the strong evidence for flatness, the question remains open in a technical sense. The measurements are limited to the observable universe, and even perfect data can't confirm the shape of space beyond what we can see. It's possible that the universe is slightly curved on scales larger than we can access. Alternatively, flatness may be a local feature, and other regions of the universe, if they exist, might have different curvatures. Curvature also connects to the idea of spatial dimensions. We experience 3 dimensions of space, but some theories in physics suggest that more may exist. These extra dimensions could be curled up at small scales, invisible to our current instruments. While such ideas belong to string theory and other advanced models, they are part of the broader effort to understand the geometry of reality. Whether space is flat or curved, how many dimensions it has, and how it connects on the largest scales, these are all part of the same puzzle. In the end, the curvature of the universe is a geometric property that shapes how light travels, how matter behaves, and how space evolves. A flat universe is one in which the rules of geometry we learn in school still apply, even across billions of light years. A curved universe would look different on those scales, though we might not notice it locally. The tools of modern cosmology, satellites, telescopes, and mathematical models allow us to explore this question with surprising precision. And while we can't see the entire universe, the part we can see tells a consistent story. The current evidence supports a flat universe. That means space, on average, does not curve in any direction. It expands uniformly, and light travels in straight lines through the fabric of space-time. This result simplifies our models and supports inflation theory. It also aligns with the idea that the universe is much larger than we can observe, possibly infinite. But as with all cosmological questions, the shape of the universe is still an open area of study. Future measurements may reveal slight curvature we missed, or confirm flatness with even greater precision. New ideas in physics might suggest other possibilities. For now, though, the best evidence points to a universe that, on the largest scales, is flat, vast, and still expanding. The idea that our universe might not be the only one has moved from philosophical speculation into scientific discussion over the past few decades. This broader view is known as the multiverse. It suggests that the universe we observe could be just one part of a much larger structure, a region with its own physical laws, surrounded by other regions, each potentially very different. While we have no direct evidence for such a structure, several lines of modern physics have pointed in its direction as a possibility worth considering. One major source of this idea comes from inflationary cosmology. Inflation is a theory about the early moments of the universe. It proposes that in the first fraction of a second after the Big Bang, space underwent an extremely rapid expansion. This process smoothed out the universe, making it nearly uniform on large scales and solving several problems in earlier cosmological models. But as the theory developed, scientists realized that inflation might not be a one-time event. Instead of stopping everywhere at once, inflation could continue in some regions while stopping in others. This leads to what's called eternal inflation. In eternal inflation, different patches of space stop inflating at different times. Each patch that stops forms a bubble universe. Inside these bubbles, inflation ends, and a more familiar expansion begins, the kind we observe in our own universe. Outside the bubbles, inflation continues. This process goes on indefinitely, with new bubble universes constantly forming within an ever-growing inflating space. Each bubble is a universe unto itself, with its own physical characteristics, depending on the specific conditions when it formed. This framework naturally gives rise to a multiverse. Each bubble may have different laws of physics, different particle types, different fundamental forces, or even different dimensions. Some may be similar to ours, while others could be radically different, so different that matter as we know it couldn't exist. The variety arises because quantum fluctuations during inflation could push different regions into different vacuum states, essentially different settings for how physics behaves. These ideas are speculative, but they emerge from models that were originally designed to explain observations we do see, like the uniformity of the cosmic microwave background and the distribution of large-scale structure. Inflation works well at describing these features. The extension to a multiverse comes from looking closely at how inflation behaves under quantum mechanics. It's not an additional theory layered on top. Rather, it's a natural result of applying inflation to all of space-time rather than just our observable patch. Another source of multiverse concepts comes from string theory. String theory attempts to unify all the fundamental forces of nature, including gravity, by modeling particles as tiny vibrating strings. One of the byproducts of this approach is the existence of many possible vacuum states, each corresponding to a different way of compactifying extra spatial dimensions. In string theory, there could be an enormous number, perhaps 10 or 500, of different low-energy configurations, each defining a different set of physical laws. This landscape of possibilities suggests that different regions of space might settle into different configurations, each giving rise to its own version of a universe. Again, this is not simply a wild idea, but a mathematical outcome of trying to reconcile quantum field theory with general relativity in a unified framework. String theory is still unconfirmed, and it may turn out to be incorrect or incomplete. But it illustrates how a multiverse might be a consequence of deeper physical laws rather than a hypothesis added from the outside. It's important to distinguish between different kinds of multiverse ideas. The kind described above, the one tied to inflation and string theory, is often called the Level 2 multiverse. It refers to regions of space beyond our observable universe, each with potentially different physical constants. There are other versions too. A Level 1 multiverse, for example, simply arises from the idea that space is infinite and matter is distributed randomly. In such a model, every possible arrangement of atoms will occur somewhere, including duplicates of our own region. This version doesn't require different physical laws, just vast amounts of space and time. There's also a Level 3 multiverse, which comes from the many worlds interpretation of quantum mechanics. According to this view, every quantum event with multiple possible outcomes results in a branching of the universe into multiple non-communicating versions. This is not a spatial multiverse, but a branching of histories, each real but inaccessible from one another. This idea is controversial and relies on a specific interpretation of quantum behavior, but it's another way the concept of multiple universes arises within known physics. Then there's the Level 4 multiverse, which proposes that all mathematical structures exist physically. In this view, any self-consistent set of mathematical rules, corresponds to a real universe. It's the most abstract and least testable form, but it underscores how far the idea of a multiverse can be extended once you remove limits on what constitutes physical reality. Despite the differences between these versions, they all share a common challenge: observability. The defining feature of a multiverse is that we cannot interact with the other universes. They lie beyond our cosmic horizon, or outside our quantum branch, or in different regions of the mathematical landscape. This makes them hard to test directly. Scientific theories generally rely on making predictions that can be confirmed or falsified. If other universes are forever out of reach, how can we treat the multiverse as science rather than speculation? This concern has led to debates among physicists and philosophers. Some argue that if a theory like inflation leads naturally to a multiverse, and inflation itself is well supported by observation, then the multiverse should be considered a valid implication. Others say that without testable predictions, it becomes more of a metaphysical idea than a physical one. There are efforts to find indirect evidence, patterns in the cosmic microwave background, for instance, that might suggest collisions between bubble universes. So far, no such evidence has been found. Still, the multiverse has a practical use in explaining one of the biggest puzzles in physics: why the laws of nature are what they are. Many aspects of our universe seem finely tuned for life. The strength of gravity, the mass of the electron, the value of dark energy. All these numbers appear to fall within narrow ranges that allow complex structures to form. If any were slightly different, stars might not form, or atoms might not hold together. Why should these values be so precise? One answer is the anthropic principle. It states that we observe these values because we live in a universe that allows observers to exist. In an infinite multiverse with all possible physical laws realized somewhere, it's not surprising that at least one region would have the right conditions for life. We find ourselves in such a region because only these regions can support complex systems capable of asking the question. This doesn't explain why the multiverse exists, but it explains why we see a life-permitting universe rather than a dead one. The anthropic argument is controversial, but it gains weight when combined with the multiverse framework. If there are indeed many universes, each with different constants, then it becomes a statistical question rather than a fine-tuning problem. Most universes would be empty and uninhabitable. A few would have conditions like ours. In this context, our universe is not surprising. It's just one among many, selected by the fact that observers exist in it. Of course, all of this rests on assumptions we can't yet test. We don't know for certain whether inflation is eternal. We don't know if string theory describes the real world. We don't even know whether the constants of nature can vary at all, or if they are fixed by some deeper principle. The multiverse is an idea on the frontier of science. It's a consequence of pushing existing theories to their limits, but it may turn out that the real universe works differently. Even if we never detect another universe, thinking about the multiverse shapes our understanding of what the universe could be. It forces us to question what counts as an explanation, what can be tested, and how far physical laws apply. It also reminds us that our observable universe might not be all there is. There may be regions with different histories, different particles, even different versions of fundamental reality, hidden beyond the reach of our instruments, but still part of the total picture. In daily life, these ideas have no practical effect, but in cosmology and theoretical physics, they help frame some of the deepest questions we can ask. Why does the universe have the properties it does? Are there limits to what we can observe? And is the reality we see the only one? For now, the multiverse remains a possibility, suggested by some of our best theories, but not yet confirmed. As our understanding grows, future discoveries may bring new clues. Until then, we observe the part of the cosmos we can see and consider the parts we cannot. Asking whether space ends feels like a straightforward question. But when examined closely, it raises another, more subtle issue. Does the question even make sense? Like many questions about the universe, this one sits at the intersection of language, experience, and physics. What we mean by end is shaped by how we navigate the world on human scales. But those concepts may not apply in the same way to space as a whole. The universe isn't just big. It may operate according to principles that don't fit neatly into our everyday understanding. In ordinary life, most things we encounter have edges. A table, a room, a road. They all have boundaries, points where the object stops and something else begins. When we ask if space ends, we often imagine something similar: a border, an edge, a place where space itself stops and something else takes over. But space is not an object placed in another space. It's not sitting on anything. It is the thing in which all positions and movements occur. That makes the idea of an edge more complicated than it first appears. To even consider whether space ends, we have to be clear about what we're talking about. There's the observable universe, the part of space from which light has had time to reach us since the beginning of the universe. That region has a boundary, but it's not a wall or an edge in space. It's a horizon created by time. Beyond it, light simply hasn't had enough time to reach us, so we can't see what lies farther. That boundary isn't physical. It's a limit on information. Then there's the universe as a whole, not just the part we can observe. This includes regions beyond our horizon, possibly stretching forever. When we ask if the universe ends, we're asking whether space has a maximum extent, whether there's a largest possible distance beyond which there is nothing. But nothing is itself a difficult concept in physics. In modern cosmology, space and time are properties of the universe, not a background it sits in. So to ask what lies beyond space is like asking what's north of the North Pole. The question contains an assumption that may not be valid. In geometry, there are shapes that are finite but don't have edges. The surface of a sphere is a simple example. If you walk in a straight line on Earth's surface, you'll never fall off an edge. You might come back to where you started, but you won't reach a boundary. The surface is finite in area but unbounded. Some models of space work the same way. The universe could be curved in such a way that it's finite in volume but has no edge, a three-dimensional analog of the two-dimensional sphere. In that case, the question of whether space ends has no clear answer because space doesn't stop. It just continues in a loop. There are also flat geometries that are finite without boundaries. A torus is one such shape. Think of the surface of a donut. A two-dimensional being living on such a surface wouldn't encounter an edge, but could keep moving in one direction and eventually return to the starting point. If the universe has a similar topology, space could be finite and yet unbounded. It would not have an end in any normal sense, even though its size would be limited. On the other hand, space could be infinite, stretching endlessly in all directions. In that case, asking whether space ends becomes like asking whether the set of numbers has a largest member. It doesn't end. It just continues, and always has more. An infinite universe may seem harder to grasp, but it may be more natural in some models of cosmology. If space is flat and doesn't loop back on itself, then the simplest extension is that it goes on forever. Still, the question persists because human intuition is shaped by boundaries. We evolved to think in terms of containers, surfaces, and walls. Even when we hear that space might be infinite, we may picture it as a really big thing placed inside something even bigger, a kind of container inside a larger reality. But that visualization breaks down at the scale of the universe. There is no outside in which space is embedded. There is only space itself, and the geometry it follows. This leads to a more refined version of the question. Not, does space end, but is space finite or infinite? That's a question cosmology can attempt to answer with measurements, models, and observations. But does space end often carries the implication of an edge, and that idea doesn't align with our best understanding of how space behaves. The confusion arises from trying to apply everyday categories to something that's not part of everyday experience. The same issue appears in other areas of physics. For example, in asking what happened before the Big Bang, we're tempted to treat time as an infinite line stretching in both directions. But according to general relativity, time and space may have begun with the Big Bang, not as an explosion in space, but as the origin of space and time itself. In that case, asking what came before is like asking what's earlier than the first second. Time may have no meaning outside the bounds of the universe. These questions reveal the limits of language and the need for precise definitions in science. The way a question is phrased can shape how we interpret the answer. When the question assumes a mental picture that doesn't match the structure of reality, it can lead to confusion. Part of the role of physics is to translate those intuitive questions into terms that can be analyzed, measured, or modeled in ways that make sense within the framework of known laws. The same caution applies when we imagine reaching the edge of space. If someone were to travel in one direction forever, would they eventually hit a wall or fall into nothing? Current theories suggest neither is likely. If the universe is finite and loops back on itself, the traveler might return to their origin. If it's infinite, they would just keep going. But the idea of a hard edge, a line where space ends and something else begins, doesn't emerge from the geometry of general relativity. It arises more from analogy with physical objects than from evidence or theory. This doesn't mean the question is meaningless. It's a valid impulse to want to understand the extent of space, just as it's natural to wonder about time, cause, or origin. These questions often lead to deeper insights. In this case, wondering whether space ends leads to exploration of curvature, topology, and the structure of space-time. It forces a distinction between what we observe and what we infer, and it helps clarify the difference between what is possible to know and what may be permanently outside the scope of observation. Science works within the limits of observation and inference. It can tell us whether space is curved, whether it appears flat, and how light behaves across vast distances. It can describe how galaxies are distributed, how the universe expands, and what patterns exist in the cosmic microwave background. From these measurements, it can build models that describe what space is like beyond the observable horizon. But science cannot answer questions that are poorly defined. Does space end may need to be rephrased before it can be addressed at all. In its strictest form, the question suggests a kind of final location, a place where space itself ceases to exist. But that's not how space operates. It doesn't sit inside anything else. It is the framework in which distance, direction, and position are defined. Without space, there is no place in which an end could occur. There's no point to move beyond. That's why some physicists compare the question to asking, "What's north of the North Pole?" The words make grammatical sense, but the concept behind them may not map onto physical reality. So while it's perfectly reasonable to ask whether space is finite or infinite, asking whether it ends requires care. It may assume a mental image that doesn't match what space actually is. The universe might have boundaries in some models, but they wouldn't be edges in the way a road has a guardrail. They might be more like mathematical limits, boundaries of applicability for our equations, rather than physical features. This doesn't reduce the significance of the question. On the contrary, it highlights how fundamental it is. It asks about the nature of existence, the structure of reality, and the limits of human understanding. It brings together geometry, physics, observation, and philosophy. And in doing so, it reminds us that some of the simplest questions can lead to the deepest insights, not because they have neat answers, but because they reshape the way we think. When we talk about the size of the universe, or whether it ends, we're usually trying to understand something much larger. How far reality extends, and whether there's a limit to what exists. For thousands of years, people have looked at the night sky and tried to grasp what lies beyond. The stars look endless. The more we see, the more it seems there is. In the modern era, telescopes have only deepened that impression. Galaxies stretch across every image, scattered across all directions. It feels like space has no boundary at all. But what does that really mean? The idea of infinity appears in science in a few different ways. Mathematically, it's a well-defined concept, a quantity larger than any number you can name. But in physical terms, infinity is harder to apply. If space is infinite, then it contains an unlimited amount of matter and energy. That seems strange, because we've never encountered anything truly infinite in the physical world. Yet some models in cosmology suggest that the universe could be infinite in size. If it has zero curvature and doesn't wrap back on itself, then there's no reason for it to stop anywhere. It just goes on. That's one of the conclusions drawn from observations of the cosmic microwave background. The light we see in every direction, left over from the early universe, shows that space is remarkably flat on large scales. Measurements from the Planck satellite and others suggest that if there is any curvature, it's very small. A flat geometry, unless it loops back in a torus or some other compact shape, implies that space doesn't end. It simply continues. Still, saying that space is infinite requires caution. We can only observe a portion of the universe, what lies within our cosmological horizon. This horizon is not a wall, but a limit defined by how far light has been able to travel since the beginning of time. Beyond that, we don't know what exists. The observable universe is about 93 billion light-years across. That's not the full extent of space. It's just the part we can see. Beyond that distance, galaxies may continue as far as the laws of physics allow. Or there may be a change in the structure of space, some new region with different properties. But no telescope can reach that far, and no information can cross the boundary of what's observable. So we build models, and in most of them, space either wraps in a loop or it continues without end. If space is infinite, that has implications for how we think about the universe. In an infinite space, every possible arrangement of matter could happen, given enough room. That leads to the idea of repeating patterns, not because of duplication, but because of probability. If matter is randomly distributed, then in an infinite space, regions similar to our own might exist far away. Not because of science fiction, but because infinity allows all possibilities to eventually occur. It's a statistical outcome. This idea isn't the same as the multiverse, where different regions may have different physical laws. Here, the laws are the same throughout space, but the configurations vary. In an infinite setting, those variations eventually repeat. It's not provable, but it's a logical result of applying randomness to infinite volume. That doesn't mean we'll ever find another Earth or a copy of ourselves. The distances involved would be far beyond any possible contact or observation. It's more of a thought result than a practical one. But infinity doesn't have to mean repetition. It can simply mean that space has no limit. You can travel forever and never reach an edge. That's a hard idea to grasp, because in human experience, every trip ends somewhere. But in the geometry of space, there doesn't have to be a stopping point. Space is defined by its contents and its structure. If those continue, space continues. And if expansion carries on as it does now, the distances between objects will keep growing. That expansion is driven by dark energy, a form of energy that fills space and causes it to stretch over time. The discovery of accelerated expansion was one of the major findings of the late 20th century. It showed that space isn't just growing, it's doing so faster over time. In a universe governed by this kind of expansion, distant galaxies will eventually move away from us faster than light can reach us. They won't disappear instantly, but they will fade, becoming unreachable. Over time, more of the universe will move beyond our horizon. In the far future, this could leave each galaxy group isolated, surrounded by darkness, with no way to detect or interact with the rest of the cosmos. The universe would still exist, and space would still be infinite if it is now. But the part we could interact with would become smaller in practical terms. That's a different kind of boundary, one created not by walls, but by the physics of light and motion. For most of human history, space was thought of as a fixed, empty background, something that just was. But in general relativity, space isn't a container. It's a dynamic, changing fabric shaped by the energy within it. The presence of mass curves space. The passage of time is affected by motion and gravity. Space is not neutral. It's an active part of how the universe evolves. So when we ask about its size or its limits, we're asking about the behavior of something that participates in the laws of physics. Even the idea of position depends on space existing. Without space, there's no direction, no movement, no separation between objects. Space isn't a thing inside the universe. It is part of what the universe is. That makes it harder to define a boundary. In order for something to end, there usually has to be something else beyond it. But there is no outside of space as we know it. That's why many cosmologists say the universe doesn't need an edge. It can just be all there is. Of course, these are still models. We can't see infinity. We can only describe it mathematically. Observations suggest that if the universe isn't infinite, it's at least very large, larger than we can currently observe. And there's no evidence of a boundary, wall, or edge. No sign that space stops. That doesn't prove infinity, but it supports the idea that space doesn't end in any obvious or measurable way. Even in finite models, the structure of space can be such that you could travel forever and never reach an edge. You might return to your starting point from the opposite direction. That's unboundedness, not infinity. But to someone inside, it feels the same. There's always more ahead. No edge appears. That's one of the reasons this question, about space ending, can be so hard to answer directly. Space may be finite but unbounded, or it may be infinite. But in both cases, it behaves in ways that don't involve a traditional edge. The study of space, its shape, and its size is ongoing. New observations refine our measurements. New theories explore how geometry and physics interact. But at the current moment, the best supported models either imply an infinite universe or one so large and smooth that it behaves as though it were infinite, for all practical purposes. If there's a boundary, it's not one we can detect. And if there's an end, it's not like any end we encounter in the physical world. This leads to a kind of quiet conclusion, not because we've answered everything, but because the question changes. Instead of asking where space ends, we begin to ask how space behaves, how far we can see, and what rules it follows. Those are questions science can explore. They don't lead to a final answer, but they provide a framework for understanding. In the end, infinity is not something we observe directly. It's a property we assign when no limit appears. And so far, space has shown no signs of stopping. It continues in all directions, governed by laws we're still learning to understand. Whether it loops back, stretches forever, or forms part of a larger multiverse, it appears, at least from where we are, to go on. Good night.